Today we're going to talk about something slightly different. This is sort of a high-end feature rather than your run-of-the-mill multiprocessor's basic demand. It's reliability, and I'll explain the reason or some of the reasons that we may want redundancy, but the redundancy for computation. So we'll see how multiprocessor can actually relatively easily provide that redundancy in the form of thread level redundancy, but it has to be done in the right way, and what one of the right ways could be. So you probably recognize this iconic image. Okay? If you don't, shame on you. You're supposed to be a computer engineer. This is ENIAC, the first general purpose electronic computer we built in the modern age, 1940s. You have to have all these modifier. I always say that. It's not the first electronic computer. It's not the first general purpose computer. I mean, people say this is the first, quote, general purpose computer. It's a stretch. It's not that general purpose, but it is a far earlier machine. I mean, we're not going back to ancient Greek. They have some contraptions that one might be calling some sort of a computer. And again, I mentioned this a lot. I use this in EC 101 for the freshmen. I asked them to name this machine. Most people turn out not to know this. In IBM's T.J. Watson Research Center, there's a replica of this in their cafeteria, so I never have trouble getting an answer from IBM people. This is the difference engine invented by Charles Babbage. I think conceived in the 1880s or thereabout. It was never completely built. It was too expensive. There's a long story about that, so I won't get into. There's a slightly useful thing about Babbage that I will allude to somewhat later. So this obviously is your kind of general purpose computer, and if you put this thing somewhat to scale, you will see that it's much better. The former, the ENIAC, weighs 30 ton, burns 160 kilowatt or thereabout, and it can perform a whopping 300 multiplications per second, not 300 million, billion, or even 300,000. 300 per second, so slightly faster than you and I. Well, not slightly faster, quite a bit faster, I should say. This machine, and if we talk about reliability, this machine has a vacuum tube burnt out about on average every 2 days, so it won't run very long. The difference engine was started, and it cost the Treasury thousands of pounds, tens of thousands of pounds, but that was in the 1800s. Translated to today's money was about a little less than $1 million. Okay, so and it's never built, and it's even slower. So we've come a long way, is I guess the story. We know that, and everybody knows the reason. It's called the Moore's Law. We have so many so many transistors, we can build more and more advanced things. So what do we get? Well, we get smaller transistors. Most of the time when we get something smaller, we get them even faster. That's a really nice side effect. And they tend to consume less power if you scale the voltage correctly. But the problem is that the interconnect, as you make them smaller, they're not improving, and therefore going to off-chip memory can be a performance bottleneck. Another thing that is a problem is the variability becomes more pronounced. You can't make two devices that are more or less the same anymore. They're very different, and because they're getting smaller, the reliability are getting less. And this is a fundamental thing. It's not a design trade-off. It takes fundamentally less energy to flip one of these transistors. So we start to worry about them. Okay, and one of the chief concern that people to just complete this thought, it's not that any of these problems are showstopper. It's that addressing all of them in the general purpose domain is the problem. Okay, so when you're designing, when you're making trade-off, it's not we can't solve a particular problem. It's that we don't want to pay too much. And one of the challenge that you hear about in the domain of reliability is particle or cosmic ray. That's sometimes referred to. What's cosmic ray? It's basically a particle coming from deep space. It could be sun. Sun produces a lot of these particles. Some of them are completely harmless, neutrinos. They pass through us. We even want to detect them. Some of them are charged particles. And from the deep space, at the center of every galaxy that we know of, there is probably a supermassive black hole, and usually they whirl around stars at relativistic speed. Stuff gets thrown out into space with ginormous energy. Okay, so this picture on the right is probably the best I kind of came up with when I'm searching the internet to show you what it really means. So these particles strike us, but thankfully we have a magnetic field that deflects a lot of these charged particles. Many of these particles are, of course, other than photons, are protons, alpha particles, basically helium, nuclei, electrons. You have these. Many of them are deflected. Okay, they have secondary impacts. So when a particle hits the atmosphere, maybe nuclear reaction happens, and then you get cascade. So by the time it reaches Earth, we're seeing a lot of secondary, tertiary, even more effects. So it's not the original particle that's from the outer space. It's this cascaded particles. There are a lot more of them, but then they have a lot less energy. So what are the energy levels of these particles? Well, it's not surprisingly, they're more in lower energy region than higher energy region. Okay, this is log scale. You can see. So we have all kinds of things: pions, muons, electrons, neutrons, whatever. Some of these can be pretty energetic. Okay, I'll tell you a story about it. So some of the energy levels, they're usually measured in eV. So 10 to the 20 is not unheard of. Electron volt, sorry. 10 to the 20 is electron volt. Now, if you still remember from your high school physics, an electron holds 1.6 times 10 to the minus 19 coulomb of charge. Okay, so a 10 to the 20s electron volt is just about, in the joule range. So this 10 to the 20s is about 16 joule. Joule is a very large unit. Okay, it's a macroscopic energy unit. The highest energy particle that was ever detected, I don't know how, I just read this online, is a particle that's called oh my god particle. It's believed to be a proton traveling at the speed of light. Essentially at the speed of light. How close to the speed of light? Well, it was said that if you send this electron or this proton after a photon, in about a year, this proton is still just a couple of nanometers behind the photon. So yeah, it was traveling. It's traveling at 50 joule. That's really a macroscopic. I mean, think about it. What does 50 joule mean? A joule is a kilogram meters squared per second squared. Okay, so 1 kilogram, your laptop, going at about 10 meters per second. I'm throwing a laptop at you. That energy is packed in one proton. So that's a lot of energy. And when that proton hits your chip, well, let's not worry about chip. That proton hits you, you're probably in trouble. So as we get smaller and smaller, the area of a device gets smaller, so you get less likely to be hit. Okay, but we put more device into it. So for the same chip area, the amount of particles coming in is going to be increasing. There's no doubt about that. Okay, so the danger is going up. Usually, we don't know per bit whether the single event rate. So these are called, by the way, single event effects. So there's single event latch up, single event gate rupture. What we like to call soft error is a single event upset. Okay, and so these things happen at a particular frequency, and so we have to measure them. We measure them in these soft error rates. So there are different studies. You can look at one of the study over here that compares different generations. As we scale the size down, what happens to the per megabit level error rate. Okay. So for the same megabit, it's going down. Why? Because the area is getting smaller, but it's not going down as fast as the shrinking in feature size. So if I have a chip and I shrink the size, so I'm going to put more, and therefore in aggregation my chip error rate is going up. This is primarily due to the effect that for the same chip area, I'm going to get the same amount of radiation at sea level. But if my chips, my individual elements are getting smaller, chances are the vulnerability, so it takes less energy to flip a bit than before. So overall, the probability of error due to this is increasing. Okay, so before you say too bad, we're going to have problems with my laptop or with my money stored in the bank. Well, you shouldn't worry too much. This is what I guess a Wall Street firm likes to buy, an IBM mainframe. When they sell a mainframe, really what they're selling, and this is one sort of example of multiprocessor, they're not really necessarily giving you the performance. As I mentioned before, sometimes people buy a multiprocessor to share the memory capacity, and some people buy them for the reliability. It's a high-end server, okay, not for the speed. In this machine, I don't know where you can see this, but I was told that even the electricity was delivered by 2 independent firms. So rest assured that your money is not going to get lost because of a bit flip. Well, and here is the thing. You are going to see a lot of errors from perhaps software, okay, and bugs in your code, whatever unexplained phenomenon. So what about hardware errors? These transient events due to particles, do they occur? Yes, they do, but they're not terribly frequently, okay? And most people don't go to the source to understand the impact. In fact, IBM had a lot of good work on this. One of the person that I cited a lot The Ziegler study published in Science back in the 1970s really studied all these. One of the plot was from his paper, this one, to study the fundamental physical effects. So when people do this kind of work, they don't necessarily go read the source. So you might hear a lot of assertions that aren't just true, that just aren't true. Okay, so you have to take that with a grain of salt. Verify your information. Don't just blindly trust quote expert, but of course you can trust me. So for the most cycles, they're not a big problem. Okay, they're far outnumbered by software bugs, or sometimes they may be called, oh, it's not a bug, it's a feature, and human operating errors. Okay? So that's it. You don't have to worry about them, period. But if you're running mission critical machine that's cleaned up, the software is cleaned up, it wasn't having a whole lot of junk, it wasn't running frivolous application, it was the mission critical machine, then fault tolerance may be useful for this mission critical machine. So for instance, your operating system, okay, it's written well, it shouldn't crash, but occasionally it does have these problems. Maybe you should have some redundancy to try to solve the problem. Okay, and if you have shared memory system, then you have to think about redundancy in the shared memory domain, and that's what we want to explain. So just to get a little bit of background, this is not a new topic. Okay, in fact, Babbage hired 2 sets of computers to do computation for him. So Babbage was really ahead of his time. He invented a whole bunch of concepts that we use today. Reliability by redundancy, yeah, he did it. Actually, he was also innovative in business practice. He hired computers. Before you think these are terms for machine, they have a human connotation before that. People who compute for you. They may be barbers, whatever, shopkeepers, and they do computation for you, and that's called outsourcing. And Babbage didn't want to do this computation, so he outsourced. And do you trust barbers doing computation? No, you don't, right? So what do? You hire 2 sets and you compare the result. Now, there lies an important lesson. If I ask you, you will know. You will hear. You will figure this out. Do you want to hire a husband and wife team or brothers team? And then you get 2 types of two sets of computation to compare result. No, you don't. Why? Because they're most likely copying off each other, so they're not independent results, right? And that's a key point that will come back somewhat later. Von Neumann, okay, the modern godfather of computation, all these machines that we're running are von Neumann machines, talked about triple modular redundancy in 1956, okay? But back then it was very unreliable vacuum tubes, so you have to have redundancy like that. Modern hardware tends to be much more reliable, so for a long time it's sort of not a problem, so we forget about all of this. Now environmental noise starts to become a problem because we are really deep into nanoscale systems. So charged particles, neutrons can interact with your nuclei and spit out ions that can impact your system. There are some radiation hardening mechanisms. Okay. For instance, using different substrate or put your system in a lead box and hope for the best. You have to do that when you're doing a space mission, for instance. But barring these special things for special purpose devices, by and large, the countermeasure is just redundancy. Okay. Information redundancy can be used in storage. You have error correction code. For logic, usually it's less of a problem than storage, but they do have errors. And mostly the redundancy comes in brute force redundancy. Do something twice, compare the result, do something 3 times, and get majority vote. And there is the problem where you need to choose the redundancy level. You don't want 2 transistors next to each other to be redundant of each other if your target demand, if your target problem is cosmic ray. Why? The key thing is why does redundancy work? The key assumption, implicit though, is independence. That I have 2 independent computations. They're not being affected by the same source error. That's why if you give a husband-wife team the number, they're not independent computations most likely. So if you have spatial redundancy, you have 2 transistors, okay, next to each other. What's happening? What's going to happen? Well, the same particle impact is probably going to impact them both in the same manner. And you don't have what redundancy will provide you, the resistance to error. How far apart do they need to be? There's various studies about this. How big is the impact radius of a cosmic ray bombardment? It could be on the orders of microns. So that's why circuit level, you ask the circuit guy to give you a new adder. This adder was so small that they fit into this this micrometer impact zone, then they're not likely to give you the result. And if you ask temporal redundancy, let's compare, and this is a very common proposal. We do some computation and we do it again immediately, check the difference. And again, this is problematic because if you have a cosmic particle event, they may last for a while. And this is, again, being measured and studied. There's a distribution, some are short, some are long, but a typical size that you can use is microsecond. So you shouldn't really compute the same result the next cycle, which is only nanoseconds away. Again, they don't necessarily give you the independence that you need. Okay? And also, suppose you have some circuit design from a circuit designer, some redundant circuit design. I want to turn them off when I'm running an application that I don't care about error. I'm I don't know, playing whatever popular game right now. Okay, so it would be very cumbersome to disable these don't care cases. So this is why I think redundancy measure should perfectly be set in at the system level. Us architects, we can, for instance, engage a redundant core. Okay, when the application is important, we allocate 2 cores. They're far apart. Okay, so they're not likely to be impacted by the same event. And I'm not using very close in time computation from the same physical device. So that's good. So this has been the choice for high-end processors. IBM's mainframe, the Z series processor is the prime example. For the longest time, they were doing lockstepping. What that means is I have 2 processors. Every cycle, they're doing exactly the same thing, and I'm observing the bus, and I compare everything from the bus. So if core A is issuing address to X, core B is issuing a read request to Y, then we have a problem. They're not in lockstep. Something must be wrong. And let's go back to the previous known good checkpoint and restart. So you see there is a problem there. Any non-determinism would immediately lead you to the loss of synchrony. So suppose I have the 2 cores, their branch predictors state are different. What do? You have no choice but to synchronize their branch predictor. So that's microarchitectural states, not just architectural state. So lockstepping is increasingly being abandoned because it's just impractical. Sometimes that's done because you have no other choice. So for instance, one of the chip that I read of was for a space mission, and they got commercial off-the-shelf components. They don't have anything they don't have the control. So what they do is they build 3 processors, and they look at the bus, and they build all the redundancy circuit outside. So that's the only thing you can do, is to make them lockstep. And then if they don't agree, you have to use very expensive mechanism to initialize the microarchitectural state. So there are some design decisions to take from these observations. So we think coarse grain is the best way to do things, meaning thread level, not instruction level at the circuit component level. And they should be decoupled. Okay, so I have 2 runs. I don't want to lockstep them. One thread should run, or one application should run, another should run on a different system, and then I somehow compare the result. Okay, and you have to compare memory accesses. Remember, I mentioned this perhaps. A microprocessor is perhaps a misnomer. It's a massive buffer, really, when it comes to it. There's lots of memory elements, cache, tables, queues inside. The real quote processing components are really small in area. And before you say, oh no, we don't have to worry about it, ECC protects them. Well, yes, it protects the pure storage. It doesn't protect the logic. So if I have an LSQ, okay, the LSQ contains storage and the corresponding logic. So if the logic is not protected, then you're in trouble. So we believe when you have memory accesses from 2 different threads, and there is proposal in the past that says, oh, just let one thread pass all the memory access to the other, then you're really bypassing all of that logic, the coherence logic, the LSQ, all of that is not being protected. And that's a big part of modern microprocessors. Okay, and if you don't have lockstep execution, then you also have a problem due to non-determinism. You run a parallel code multiple times, they may not necessarily execute in the same way. Okay, there's non-determinism, and when that happens, the 2 redundant form of computation may disagree on the result. So you have to manage that. Okay, so that is something to be worried about. Now I'll explain one approach. Of course, that's my proposal, and of course I think it's logical. That's why I propose it. So next time I'll explain one possible way of doing it and contrast that to some other different proposals.